for me to give my introduction before we start. So we're very fortunate to have Luca, Giuggioli?
Giuggioli, very good, very good.
Thank you. Luca works on interacting entities from animals, molecules, to random walkers. He's published widely in statistical physics literature, in ecology, particularly movement ecology, and has also published on robotics, and always in very top journals that I recognize from those fields. So it's very important interdisciplinary work that he's doing here, and it's always very exciting to see this sort of work. I think that's one of the main reasons why the JGI cross-faculty activities are trying to grow this direction of work. So I've already seen Luca speak on different subjects a couple of times before, and it's always been a treat. So without ado, please take it away. Thanks very much, Luca.
Thank you. You hear me? Everybody hears me, correct? Yeah, perfect. So, well, thank you so much, Daniel, and the Giuggioli Institute and Heilbronn Institute. I guess I'd like to thank everybody for the opportunity, and I have to say this is I think it's my second webinar ever. So I know in the first one, as I was saying, Daniel, that it was difficult to make jokes. I'll try, but I think they're not going to have the same effect as when I'm in a room. So I just hope for the next occasion to be all together, but I still will enjoy anyway, talking about what and the potential application and collaboration that can emerge out of this. So once again, thank you, Daniel. So, okay, so let me start before I forget. Oops, no, yeah, I have to do there. Okay, so before I forget, let me just thank my group here. Well, actually, the last one, the Zohar, I just put you, because I know you are there, Zohar. I just put you one line below because there's nothing of the thing that you are involved directly, but since we want to apply many of the stuff I'm going to talk about in your robotic problems, so I think it's fair to thank you as well. The others are the one that you will see in the reference at the end. They are all named there. And Deborah Dash is a postdoc in my group. Then Toby and Shri are PhD students. Tom was a former PhD student. Okay, so let me see the outline here. So what do I have to tell you is that I want to tell you especially about discrete space and time, although let me just say that time discrete is not essential. It could be continuous time, but you will see most cases that I'll formulate the problem also discrete time. But I'm going to tell you why we want to model movement and interaction in discrete time and space. What's the convenience? I'm going to talk to you about modeling events of interaction, some specific one, and why it's convenient to distinguish them between reacting and inert interaction events. Probably by the names you already understand what I mean, but be specific. Then I'll tell you about some of the challenging problem that has been always around about computing, mean time and probability of interaction when there were many things happening at the same time. In this case, let's assume the target is static, so this is a multi-target environment. So then you talk about encountering some points, but although you can also talk about individuals moving, and then you have lots of points where they can encounter each other in a bigger space. It's a still static target, but in a much bigger space. And then I can pass up something which you will see. It's about transmission of disease, for example, that I'm going to talk about. So these are the reactive interaction. Now, the inert interaction is something I've been involved more recently. It's about, once again, how do you compute and calculate quantities, usually in transport processes, once movement happens in an environment which is disorder, but the sort of disorder where you bump into things, you have to move around, and you just have permeable barriers, open gates, partial partitioning, and so on. So for this sort of objects. And now on the specific, which is not discrete space, I'll show you that actually one convenience of working with discrete space is that you can actually take limits sort of straightforwardly and get the equation in continuous space, continuous time And then you find out that, interestingly, there are new equation, and this is one case I'm going to tell you about, the Smoluchowski, sorry, which is, we have a new equation which deals with permeable barriers. I'll just briefly mention how you can go beyond what we have done so far and try to condition to the number of these in certain locations. Then all of this was Markov. Then suppose that you have some degree of non-Markovianity. Suppose that you have some correlation in the movement. And, I'm working at the moment on modeling and tackling the problem of correlated movement in confined space. Now, I mean, probably I don't even know if I reached correlation, but then I'll tell you, if I'm really lucky that I have time, I'll tell you about moving on an hexagon. So we have solved the problem of in an hexagonal space, how do you actually represent the propagator, I mean, the green function. So this is a big challenge to tell you all of this, but I'll keep track of the time and then I'll stop when I go too much over time. Okay, so now if we ask the question, why in the past, I mean, this continuous space, continuous time has been so successful, then we should actually imagine that the reason has been that lots of symmetries can be exploited, and then you can solve analytical problem, and then, from translation invariance, radial symmetry, and so on, and that helps so much get insights into the problem itself. And, we have an infinite number of examples for that. So in this context, we are talking about movement, random movement. So we all know about the diffusion equation. Let's think about the 2D case, because I've talked mainly about 2D case. Now, clearly, we all know about the diffusion equation, and we all know that it's relatively straightforward to solve it. And again, what in this case, you Fourier transform because you exploit, the translation invariance. So, and then you find the solution, you invert, and then you get your solution. So in other words, no problem if there are no special boundary point, because we exploit these symmetries. But once we start losing symmetries, then we get into trouble. Things become a bit more complicated. So now, if you think about this 1D, there are lots of problems which you'll hear me talk about. Maybe not the radiation, the third one, but certainly, you have the Dirichlet, the Neumann, and you have the leather, which is actually the permeable boundary condition, which is a bit less known, but that's material science is often used. So now, of course, in 1D, this problem can be solved just with a simple diffusion. But as soon as you are in higher dimension, then it becomes a real challenge. First of all, you can't really talk about a point. You have to talk about segments, and you've lost all sorts of symmetries. Now, to be more precise, let me just show you here example of what I want to talk to you about. So imagine you have an escape problems, and now notice I'm making discrete on purpose. So you have a walker, and now we have multiple points where as soon as you reach, you are safe. Let's say if you are really running away from a predator, for example. So in that context, if you try to have segments on those boundaries which represent the region where you can escape, of course you can't really solve. You have to solve it numerically. Another problem, imagine you have this is the first classical first passer problem, a searcher which is looking for, this is a forager actually, looking for food items. There are many, they are not on the boundary, so not, it's not what you would call an escape problem, but you certainly would be interesting to find out what's the time it takes to get to any of those. And then, of course, if you are in higher, in continuous space, you have to, each of these, you have to create some little disk, and then with, maybe a small value of the radius, and then it's a complicated, it's unwieldy boundary value problem, no? Now, if you go to transmission and counter problems, now suddenly these are two individuals which are in two areas which are not fully overlapping. There is only a partial overlap. Now you have lots of points where you can have interaction, in this case, an encounter, or in principle, when they meet, they could pass an infection. So this is a transmission problem. And so trying to solve that problem, it gets in continuous space, it's not possible. And this is the case of other problem of permeable barriers that you can see there, impenetrable barrier in the middle of a domain, and there's some area of lower diffusivity, and so on and so forth. So now clearly, if I would give you the way to solve this problem exactly, then of course you just say, okay, so why do we even try to solve it, with variable which are continuous, of course, because the other one you cannot. So, and this specifically, as I was telling you at the beginning, the reactive interaction is the 3 example there, and then the one which I'm telling you about is permeable barrier, low diffusivity. So these are the inert interactions. So I'll tell you a bit about all of this, a bit of math that you will see, but also examples. So now, so what is the fundamental tool that one is interested in computing these interaction events? Is about, imagine you have a searcher and you have a target. Let's consider a single target. For those that don't know, you can imagine building lots of trajectories that reach R for the first time. And then the way you build, and find the first passage is that you sort of do a tautology, so which is a renewal thinking, is that your probability that you are at R0, let's see. You see my cursor? I imagine you see my cursor. Yeah. The probability that you start at R0, that you are at R, which is your target at time t, is equal to your first passage, which are this trajectory representing the first passage. They go from R0, and then eventually you hit there for the first time, R, at some earlier time, t prime. And then once you're there, be Markov, you start there, you've forgotten where you came from and so on, and then you can just move around, and you're interested in coming back at R some later time, which is time t, because it was defined there. And so that therefore they are independent, you multiply, you have the probability that you start at R, you are back at R in the difference in time between t and minus t prime, because you were at t prime. And so that's how you actually relate to your t. And now, of course, this t prime can be any number. So you sum over. Now this is a discrete version, so you sum from t prime from 0 to t. So that's a renewal equation. And once you see that there is, this form which is difference in t minus t prime, so it's a convolution-like form. So in discrete, you just use the generating function, which is the same as the Laplace, just in discrete. And you actually, so you will see that when I have the symbol tilde, this is about Laplace, generating function or Laplace. And so, this is, becomes an algebraic relation. You can take P on this side, P on that side, and that's how you get the first pass probability. So it's a ratio of the solution of the problem, which is P R0 to R0, so what you call the propagator, the green function. So wherever you start, wherever you get, and this is a generating function. So you need the ratio of those two generating functions. And now, out of that, sometimes it's very useful to get a mean time of that first passage for hitting time probability. And yeah, it's an easy algebraic exercise to do the derivative and put in Z1, so you get the mean time. So this is very well known, and this is for one target. Now, suppose that the other way of computing this, which is, imagine that you consider the survival probability. So now one of the targets is considered absorbing. So the actual target, now it's an absorbing point. So you solve the problem by thinking that you solve the diffusion equation, in this case in discrete space, discrete time, but then with the point R, which is absorbing. So now notice that what I'm using here, this is a survival. Your P now is a calligraphic P. So it has a different shape because this is a solution which has an absorbing point at V equal R, okay? So it's not the same P as before, but you can actually relate the survival to your first passage, trivial ways. And then the first passage, therefore, you can actually go through the renewal, you get the ratio of the solution of diffusive problem without any special point, and you just are interested on a specific point R, which is your target, or you go through the survival formulation, and then your first passage, you sum over this P, which you notice is different P, because that's a solution with the absorbing point. So this is for one target, things are well known, and that's the typical two ways of doing it. So now what happens? Why is it that we have not found many cases where people have studied this problem in discrete? Well, it turns out that finding the solution, the explicit spatial-temporal solution, has been a challenge. And mainly because the discrete analog is a bit more complicated than continuous space. So this is just to show you. In this case, you have t+1 on the left, and these are two direction n and m. So you have a probability q, which is a probability 1 minus q, the probability of staying, and then you q over 4, so that you conserve probability. Then you have your jump. Suppose n is a horizontal axis, you come from the right, this you come from the left, and this you come from above, you come from below. No? So now solving that problem, if you add discrete continuous variable, it's very simple. The reason being they factorize. So you essentially have two one-dimensional problems. But now it turns out that this does not factorize, and therefore has been a challenge. Now, in principle, you might think, well, we can talk about the unbounded case because, the unbounded solution was known. I mean, it's known in discrete. I mean, the only thing is that many quantities that where you are interested in computing means, once you don't have boundaries, then becomes infinite. So there is not so much utility in those. So finding the solution in bounded domain was sort of a challenge, and it was useful. And so this was a paper that I published in 2020. So I worried about finding solution in arbitrary dimension for the discrete lattice random walk. Indeed, that example before was just a 2D version. And so essentially I was interested in the case where, you have reflecting boundaries, periodic boundary, mixed boundary, absorbing boundary, and so on. So some of these cases in 1D were known also in higher dimension. The periodic was known, the absorption as well, I think in 1 or 2D. But the reflecting and the mix were probably the one which were known. And so the way, just to tell you without going to the details, but the way you try to solve it, you sort of do a hierarchical constructor from lower dimension to higher dimension. And so imagine that I show you for the diffusion in reflecting boundaries. Suppose you have this problem to solve. Then instead of solving this problem because you don't know how to solve it, so you just say, okay, let me solve this separate problem where I just bound one direction and not the other one. So, and since you know the solution in 1D problem, so what you do, you do a Fourier transform along that axis so that you get a solution which is an effective one-dimensional equation. So, and so you consider a semi-bounded case, so you Fourier transform, so now you see it's an equation only in n, k is, it's just a parameter here. You solve that, you take the generating function, and then you solve, and you invert, you solve in Fourier on one axis and in space along this axis. Then you invert it in the, you do an inversion in Fourier, you get the solution in open space, and then you use a method borrowed from electrostatics, which is a method of image, to bound back the space here. So now you get a solution which is a generating function in both directions. Now, I had to develop a Chebyshev polynomials identity with some new identity so that I could actually write as a finite series. And then eventually you invert it. And then you can see now, as you can see, these two cosine are summed up inside this power t. So that's why, the propagator are not the product one with respect to the other. Okay. So this is just the example for this case. And then you can build this up. Now you have a 2D solution. You just think about, you have a 3D problem which is bounded. You just imagine that the third direction is unbounded. If you transform, you come back and you know already the solution in 2D, you use it here. And inside here, what happens, the coefficient will change because you have some Fourier of the third direction and so on and so forth, okay? So now, how did we use this for the case for multiple target? If you are interested in having two possible targets. So imagine this is, I'll show you that the case that you have R and R prime as target, you start from R0. Once again, you build this, you have all the first trajectory they go to R prime, but then there are, if you consider those, and you have to, okay, sorry, I have to resay. So you start from R0, you have first passes to R prime, which is this one, this quantity here. But then if you consider only the first passes to R prime, then there are all the other trajectories that go through R first and then go to R prime. So this quantity G is the first passer from R0 to R prime at some, sorry, this should be at some time T, given that you have not been at R, okay? So therefore you construct it from the first passage from R0 to R prime. But then you have to subtract all those trajectories like in red, which are the one here in red, which has gone there first to R before going to R prime. And so, and the way that is built is again to the same object, which is this G, which I call G1. You go from R0 to R at some earlier time, and you've never been at R prime. So it's the other one, no? And then you go from f of r, because we have been here to r prime, as you know, in the time t minus t prime. So I mean, you play this game, you just think about swapping these two directions from r0 to r and not r prime, instead of from r0 to r prime and not r. So you get two equations on gr01, where r and r prime are swapped. And so essentially what you get, which is this one, and then what you get a first passer to either two targets. And so if you want, then now, once again, what you can see here, everything is reduced to the first passage of individual targets. And so that's the convenience. In fact, you know, if you compute the mean first passer to either of these two targets, well, actually, this was known in the past. It's made up of contribution of individual first passer from R0 to R, R0 to R prime, and so on. Okay, so this is the case of two targets. Now, before I go to the n target case, I told you that we talk about reactivity, but when you have reaction, it means you don't have simply absorbing point, you might have partial absorption. So what does it mean? So what is known, what has been known so far about reactivity or targets which are partially reacting is that there are two limits, two well-known limits, which are the motion limited and the reaction limited case. So imagine that you have a searcher which is looking for a target, and then suppose that you have some, let's suppose you have some rate of encountering this target. And then once is in proximity or upon the target, then you have some reaction rate P. So the general assumption that people have always used is that it's widely used in different contexts, is that you sum the rates. But I mean, I want to stress the point that this is also, I mean, used, for example, in quantum mechanics, Matheson's rule, or the inverse addition law for chemical compounds reaction and so on. So it's widely used, but it can only be valid in special cases, obviously, and you will see why when I do the many targets scenario. But what are the motion limited? Well, this is one of those cases where it's very valid. So if, you know, the reaction, I mean, the encounter rate is much smaller than the reaction time, all that matter is that, you know, so this one goes to zero. So all that matter is that you are so fast onto the target that all that matter, sorry, the other way, you are, so this is the case of the absorbing point, no? So that's the case where as soon as you reach there, then it's the first passer problem only, no? So that's one case. So you can imagine if this one be sufficiently large, then essentially it's a first passer problem. So all that matter is that rate. But the reaction limit is that if once you're on the target, everything gets very slow, so then most likely what happens is that you are always consider yourself onto the target. All that matters is the reaction once you're on the target. And so that's the other limit. Now there is one more case where actually you can think about that the sort of formula is correct. And this is like if you have a single reactive target, and suppose you call it reactivity rho. So you can solve precisely that problem. And then you can show that the mean reaction time, so the overall reaction time, which has to do with the movement and the reaction once upon the target, is the reaction rate. So now it's of this form, if you think about. And now here, what you notice, what you have here, you have something related to the reactivity probability, rho is a probability in this case, and the mean return to the target. So it makes sense. So you can think about that. I'm a searcher. You know, if I get there and then in a certain amount of time on average, then once I'm there, if I don't get immediately absorbed, then eventually what matters is now I'm starting from there. What matters is that the mean time for me to return multiplied by this factor. So although notice that despite here we talked about having a reaction rate, there is already a mixture here of the term, which is a movement aspect, and this 1 minus rho over rho, which has to do with the reactivity of the target. No? So it's still of the form that you sum two rates, but you know there is already a mixture. In fact, you know what you see, the general answer is that you have all sorts of combination of this quantity. So now imagine that you have many targets. So the way to go about the many targets is think about splitting probabilities. So what are these quantities? So it's a probability to reach a specific target among the, let's say, M for the first time, and none of the others. So if you do the math, it turns out that you reduce, it's a generating function reduction, and then you do the so-called, you use the so-called defect techniques. You essentially have a matrix problem, so you solve via Cramer's rule. And so what are these matrices? They contain first passage, individual first passage from the target Rj to the target Ri, and it's their generating function. The diagonal elements of these two matrices, actually, I'm talking about the matrix F, sorry, is like it contains the return probability, as you saw in the first case when there was one target. That's clearly as important. And then once again, you see this factor 1 minus rho over rho, and they could be all different for each target. They don't have to be of just a given type. And then, you know, this again, it's a Kramer problem, so you can recognize that you have to pick, I mean, the kth element there and take the first passer from the starting point to all the targets and take the transverse and so on. So now the first passer probability to either, sorry, to any, is in English, it's any of the targets, is for you sum over all the splitting and you get your answer. So now I want to show you that, I mean, not to go into the details, but just to show you that if you actually go for two targets with two different reactivity, rho R1, rho R2 here, then you see it's quite a complicated object. And then even just the mean first passage, as you can see, you might recognize there is a structure here, which is the one related to this one divided by this quantity, which is a first passage to other two targets. But then you see lots of other terms, you know, you have even the quantity of return probability. So it's a very complicated object. So in other words, has nothing to do with, you know, the assumption 1 over E plus 1 over V. And, you know, it just happens that in one target you have that situation. So, so what do we do with all of this? Okay, sorry, this is a general, completely general answer for the determinant. So in this case, for the mean first passage, you have from a target Rj to Ri, so you have sort of the permutation of all these targets, mean first passage. Along the diagonal, these elements are containing the return probability at R multiplied by this factor, which represents the reactivity. And then the T1 matrix is just T minus 1. And the T0 is the one on top where there is initial condition dependence, okay? So just to show you that in this case, I think this was a 4-dimensional space. There were just 3 targets. And the Q here represents, I don't know if you recall, the probability has to do with the probability of moving. So 1 mono Q is a probability of not moving. So this fellow is the one which is always moving. And this is, you know, not the case. And it's 4-dimensional space, 3 targets, and we are moving one component, one axis of one target from 1 to 21, I think it was, yeah, 4D square of size 21. And even after 10 to the 7 simulation, you don't get, you know, the actual analytic result. I mean, okay, so you get close, but so this is just to show you that everything works when you compare to simulation. Now let's think about how to use this one. First, I'll do some simple applications. Some will be, the later on will be a bit more biological when I talk about inert. So let's think about a predator-prey game. So, and you can ask the question, in this case, you want to exploit the imperfect capture of the predator to sort of guess if there are interesting strategies to follow. So this problem that you have looked at, you have a predator and has a bias to go toward that corner, and then it starts there. That's the starting point. And then you have the prey, which starts in the middle of its own, let's call it home range. Now the predator doesn't see this boundary. On the other hand, the prey remains inside here. Huh? So then the predator will go towards that, and the prey can choose the angle theta, which is the strategy. So it's a very simple problem because, you know, these are diffusive walker. There is not a real predator-prey scenario as we might call it. So, but you may think about if the probability of capture is very high, so it's like an absorption problem, so perfect capture, then the prey should stay as far as possible and the most time away from the predator to minimize the time to be captured. So, and therefore, if you have theta 0 is convenient when rho, the reactivity, which in this case would be the capture probability, is 1. On the other hand, if the capture probability is small, you might think that you better go towards the predator, because if you get missed the first time, then this fellow will go on the other opposite direction, and then you stay mostly on this case. Now, eventually you get captured because it's a finite space, okay? So the mean capture time eventually will be finite, but that you can think about that if you actually, there was a real, more biological, realistic scenario, there might have been an escape point here, then probably that's what you would try. Huh? So in fact, if you now use that, notice that here now the number of encounter position are all inside here. And you have this row for each of these location, it's the same, but you know, it could be 1, 0, 8, 0, 8 here. From between these two, we have changed the diffusivity of the predator and the prey, and here you have, you know, the row 0, 0. So the chance of being captured at the first occasion is tiny. Okay. So notice that, as I was telling you, when rho is large, you are certain to be captured as you meet the predator. Then, you know, the best strategy is that theta is 0. Okay. So you exchange, you go down there. So you stay as much as you can in time away from the predator, which is coming eventually at you. But notice that the opposite one is that, exactly, I was telling you, if rho is very tiny, then you better, you know, maximize the mean time to get captured as you go towards the predator. And now, interesting, I mean, this is a transition, and you know, and there is interesting, the transition happens with, you know, you have this double peak, I mean, so double dip that develops, and then eventually this, notice the number here very tiny. So yeah, if you try to get this out of simulation, you can wait and wait and wait, and you'll never see these features anyway. So now then these points that you see here are actually, given that we had the exact results, we develop a better motion limited first order approximation reaction limited, and you can see that in this specific example they're not too bad. This is so this is a reaction limited, which is indeed when rho is pretty small, that's what happens. And this actually the motion limited, which is first order motion limited approximation. I'm not going to show you what they are, but you know, that's okay. That's one example I wanted to show you. Now this is a maybe more interesting example for many of us, having had 2 years of COVID. So suppose that you have this problem. Now suddenly you have two individuals that they meet, and the green one is the susceptible, and the you know, the red one is the infected. So once they meet, they pass COVID or something else. Okay. So, and then they keep on going, doing their own normal life. So now again, the way you would compute this probability is the same that what I showed you before. Now the targets R1 or 2 arm is all the space where these two individuals can meet. So if you just assume the spatial uniform, so I'm missing an I here, passing the infection upon meeting, then so instead of having a vector row, you have a single row, and then you can compute the time-dependent pathogen transmission upon encounter. And so then I show you here a couple of examples. So that's the rho equal 1, remember, it's just an encounter problem. And these are the two lattices we use. So this is a periodic one, the red one, and this is a reflecting one. And so now this is a regime which you are getting into the regime, which is the motion, the reaction limited regime. And so that's why actually here over a long extended period of time, I mean, the probability is uniform. Now, and the peak, the mode here, all related to the fast trajectory. Now, in this case, I forgot now the exact size of the domain, but they were starting at opposite ends, opposite corner. So in the periodic, they can meet right away because they're exactly opposite corners, so they're next to each other. So that's why the periodic was going up very quickly. And then by the time eventually you occupy most of the domain, which is when this one starts declining really quickly, that's where the first trajectories of the reflecting start meeting. In fact, I think I have a little video. Yeah. So if I show you the video, it's a much smaller domain, it's 6 by 6, but these are the starting location. Now that I showed you was actually the overall probability of transmission. Now here you can actually have a specific spatio-temporal association, and will be color. The color here will be about representing the probability of being of capturing the disease, the pathogen, while these curves are the overall. No, so let me see if it works. Yeah. So as you can see, those are the one or the periodic that actually immediately get capture, and then eventually here, the probability when it goes higher on the overall, it's this location in the middle that, you know, you have to wait enough time for this particle to diffuse to get in the middle. So yeah. Okay, so this again is possible because you have all the splitting probabilities that you can work with. So now let me see, you can push this and ask the question in the context of COVID. Now, are not in a spatial explicit content is generally not computed. I mean, it's also a concept about the population, but you can try to, you know, compute it out of the population, out of these quantities now. And suppose you have an SIR situation. So an individual is susceptible, you have a population of one infected, the population of susceptible, which can also recover once they become infected. And then you can ask the question, what's the probability of passing the infection? Now, gamma, which is a probability of recovery, is, yeah, you can think about that. Either you get out of your system if it's a 2D system. So you can think about, I'm going to a supermarket and then I have some rate of getting out, or really it's a rate of, you know, of losing the infection. No. Now again, R0, remember, it's not RT. R0 is about in an initial case where you want to just look at the secondary infection from one individual. So therefore, it's actually it's really a two-body problem only, even if you have a population of individuals. And so this basic reconnection number, you can connect directly to this transmission probability. Now, interestingly, you don't even have to invert this function because, you know, but you need the probability and you evaluate that at 1 minus gamma. And these are the number of susceptible, and this is the domain size. And okay, so we looked at how it's the dependence on gamma, and we could actually compute it. And apparently, you know, it's in the epidemiological literature. It's not really something that people are used to see because you don't do explicit calculation or R0 in space. So now, so far I told you about reactive interaction. So let's talk about inert, which I mentioned at the beginning. And so now, what do we mean by inert interactions? And so the way we talk about and we compute these inert interactions is about modifying the transition probability. Now, the difference is that for the previous case, mathematically speaking, is that the reactive on a probability function like this one, you add terms, I mean, you subtract terms because it's non-probability preserving. All the inert one are the one which are probability preserving. So as I said at the beginning, you can think about that I have a permeable barrier, so I go through or not. I mean, I'm not getting absorbed, or I mean, there's a partition through which I can go through and I have to go around. So these are, and therefore the easy way is you just modify this transition probability. If A represents the standard transition probability, you just it's a pairwise things. You can think about U and V, which are the two nearest neighbors, for example, and you modify with this lambda. So you take away some probability, but actually lambda, we just build it completely general, it could be also negative. And then in principle, you can have also long range. You sort of have the general possibilities. So examples, you know, you can have a long range connection between U and S. So you take from the probability of staying, you draw from that because, you know, you want to preserve probability, and then you just connect S and U in this way. Now you see that's why this arrow has become that, and that one has become that, for example. Now a sticky site, so it's a site where, notice that I change the thickness of this line. So as I reach W, I make this line, which are the ability to move to the nearest neighbor, thinner. So I reduce the probability there and I put it onto W. So then now there is a higher chance of staying. So therefore, that's what we call it sticky. Now, again, if you go and solve this problem, yeah, it's a bit more algebra than the reactive cases, because all the propagators you need, as you can see, since it's a pairwise things, it's a difference of propagator. So it's a bit more involved, but fundamentally you rewrite it as, and you solve it. And this is the actual propagator with all the inner side is given by the one without, plus all this information about where you start, where these defects in R, the many there are, which are all these changes that you have created, are inside here. So again, for each pair of changes, you're going to have increasing the dimension of these matrices. Okay, so just to give you an idea, so in visually, so these are the sort of problems we thought, okay, let's think about solving this problem. So notice that now we can deal with all sorts of shapes. This is a very funny shape, that you have of this. There is also a vacuum here that you can reach. So, and we have no problem of tackling this. In fact, I mean, you just need a few seconds to just plot the probability as a time t100. This is okay, it's a small domain, it's 10 by 10, but as you can see, this is a starting point. This barrier, which is impenetrable, as the worker is diffusing in this case, eventually remains trapped there a little bit, no? As expected. Now, in this case, where you have the sticky sides, now here you see the probability that you are there sometime t100 is a bit higher than the one surrounding it, and so on. So, yeah, so suppose that you are looking at this problem, you have a 2D squared domain with n random distributed permeable barriers and anti-barriers. What's interesting about this one is that now imagine we have one starting location, we have a 2D domain with perfectly absorbing barrier, and then we start putting this barrier or anti-barrier. What do I mean by anti-barrier? It means instead of slowing down, I'm just whisking through. No? So I'm going, so that those transition, those lambda that I was telling you about, instead of being positive, they become negative. No? So then, and we can play with this and look at the exit probability, because it's a 2D exit probability relative to the exit probability without barriers. And then you can play with lambda. And so one case is a reflecting barrier, and this is a number of randomly placed barrier. And of course, if you really go beyond a certain value here, then you're going to hit percolation, obviously. So what was interesting to see, the asymmetry in these two curves clearly is expected to be asymmetric, but this are not refraining the worker to reach the absorbing barrier. Another problem I wanted to tell you is that I remember talking about trying very hard to use continuous variable and eventually, admitting defeat. Back then, like 5 years ago, even more, I tried to model a thigmotaxis. And so what is thigmotaxis? So probably this is, you can see what it is that the tendency of animal to stay close to boundaries of a domain or a wall. No? So in fact, this is from, actually I pick it up from this paper. It's a high resolution, 2 frames per second, 5-6 hour experiment. This is a single animal, and they follow it, they track it, and then you can see the high density of this individual staying around the boundaries here. No? Actually, you have Matt Jones also gave me some data about his one experiment some years back that he had on rat movement data on a half a meter circular arena. And again, this is another one high resolution, and you can see that even in that case, I mean, for other reason, probably the rat, kind of afraid to be in the middle, I guess. But so you can see also it's sort of common in many situations in the animal kingdom. And so I tried very hard to solve this problem with continuous variable. I didn't succeed. And so, and then we decided, okay, let's try to solve it here, because why do we think that this is easy problem to solve in this context? Because imagine if you just take your arena, and you'll see, although we have Euclidean lattice, we manage also to create such a similar shape. And now this alpha in represent the probability to move inward from the outer region. And so, and this is a region where the animal might stay much longer. So we allow the animal to move through this as if there was nothing, no barrier. And now suddenly the alpha in to come back in is what makes it harder. And therefore you have a higher chance of remaining outside. So remember your lambda in this case, which is the one that modifies the original AUV, because it's AUV minus lambda UV. Then you multiply this by, so if you put alpha in 0, there is no outreach. So it's a simple diffusive problem. Now, alpha in 1, it makes you make it completely 0, your ability to come in. So that becomes a reflecting boundary. And so we looked at playing with this alpha in parameter. And so just to amaze you that although it's an Euclidean lattice, then we actually managed to look at the dynamics here in circular domains. And what's interesting is that you can see that since what we have done, we have made this transition rate asymmetric. So somehow we push the system out of equilibrium. So instead of expecting a uniform distribution here, at the end, at long times, you get, these step functions, there. And you can, well, let me skip this one, otherwise I won't have the time to tell you the other thing. Okay. So now another thing that we are interested, and this is sort of exploratory, is that imagine the problem of delivering a drug through the epidermis. And there are recent publications we have found that are interested about optimizing this process. Now, it's a quite complicated process, so this is really a way to see potentially if it can be useful what we have developed. Now, there are different ways for which you can reach, the inside of the body through the epidermis, but in particular, we are interested in this one, the transepidermal intercellular, which is the one that goes through this brick and mortar shape of the epidermis. And I don't want to go into the details of why that's the case, but there are discussions. These are theoretical discussions from the medical community. What if we pierce a little bit the the epidermis, and how much faster can we reach in here? No, and so it's like a first pass problem. No, so how do you enhance the drug absorption by using microneedle piercing of the epidermis? And so we thought about, okay, why not, seeing what we can provide in this context. And so you can imagine that this is a brick and mortar structure, and then if you pierce, okay, again, this is a one that we would need really discussion with, a real medical practitioner if that's really the case. We pierce it with, an object which has h height and with w in such a way that now suddenly your walker, that would be the diffusing drug. Now it can have free access here, and then of course, but then it gets trapped here, although it will still have the access of going through this, as you can see here. No? And what was interesting to see, depending on the size of h and w, is that, so just think about this, we are changing h, so we are making this deeper and deeper. And now when, h is 0, so this value, where is it, around 8, that will be the time it takes, to go through this, through this, like you see here, no, the average time. And now, depending on how much you pierce, then you can see that you want to pierce enough so that you can get to values which are lower to get, to get your drug down here. So it could be something interesting to further develop. Now, another thing I wanted to tell you is that although I'm telling you about inert interaction, now, although we can also, since it's very general, we can also think that some sort of particle-particle interaction can be treated by representing them in a bigger space, in a higher dimensional space, but by imposing certain asymmetry on the environment in terms of their ability to move. No? And so let me just be specific here. So this was related to the search of promoter region on DNA by transcription factor. So it's a one-dimensional problem. Two transcription factors have to meet to get to a specific target. So if they go to the target by themselves, it's no use. But if they meet, they bind, and they could also unbind, and then they reach the target along this one, one-dimensional DNA. So essentially, it's a two-dimensional problem. And so the way we treat this problem is that when they are bound, this particle in this two-dimensional space, they move probably, they move slower because they're heavier. That's at least what we assume. And then when they are, on the other hand, so this is, imagine you have a two-dimensional space, these are the lattice. And then when they are not here, it means they're not bounded. And so the two particles are freely, they are independent, so they're freely moving in their own space. And in fact, in some sense, what I'm representing, the two particles A and B, this is on their own individual 1D system. But then when they come onto here, they have, now it's a combined particle, it's a complex particle, and they have an ability to move, which is, of course, it's reduced and based on this factor. So what is this factor R? When you try to get to the answer, this is like, so this is proportional to the diffusivity of bound bound particles. So if you just increase along these two axes, and this, if you go this way, is a probability of unbinding. And then for each of these A, B, C, D, you have a probability of, it's proportional to a probability of binding. Now I say proportional because the way you build the model, you always have to multiply by the movement, but that's just a complication in building a model. So now there was a reactive study at 100, 100. The starting location was in nearly opposite, 100. So one was 1, one was 100. So, and what's interesting about these plots, when you see these curves that actually have a bending here, like this one and all of this, it means that you can find a minimum, a relative minimum here for a given, for multiple values of the proportionality to unbinding relative to the diffusivity of the bound particle. Okay, so again, this is to show you that you can look at mean first heating time in this context of particle-particle interaction by modifying the space in high dimension and thinking about inert interaction, and therefore, and then looking at first heating time. Now, this is okay. I don't think I have so much time, but maybe let me just tell you about this. This is something that, you know, we are still very surprised by. Now we have understood, but and that would be perfect if we were in a room, because I would query everybody, every of you, if they would give me the right answer. So imagine that I have a one-dimensional problem, and then I'm starting at n0, I mean diffusing particle, and I put a permeable barrier between you and u plus 1. No? So it's to the left. This is a reflecting barrier, and then you ask the question. It's a first heating problem to go to n. So then what I would ask is that, I mean, where do you think is best to put this permeable barrier? You know, closer here or closer to n0 to minimize the time. So now, of course, again, I can't really play with you in the room, but yeah. So let me just. I can write you the probability. You can write the probability, and it's different depending on you being to the left or to the right. So just focus on this one. And this A and B are Chebyshev polynomials. So I'm not going to discuss what they are. Now, the only parameter dependence on the way the strength of the permeable barrier is this lambda, is in this factor here. The position of the permeable barrier, which is between u and u plus 1, is here on the B factors. And then you can think, and so again, I can tell you the surprising part is that, of course, the probability does depend on you, on the position where it is, but the mean does not. If you compute the mean, you just have the first passage irrespective of, I mean, without the barrier, and then it's 0 here, as you can see. So the mean is completely irrelevant. And so the way you can try to interpret is in a physical way, before you do the math, is that, you know, what happens here, I mean, it's still magic to some extent, is that you can imagine if you put the barrier here close to n0, then once the barrier has first trajectory, the fast one, that get clearly push the particle to get to n. But then there are the ones that go through, that stay for a long time on this side. And if there is a big space here, then of course they stay for a long time. So in both cases, you can increase quickly the probability of the fast particle. So the mode of the probability will increase compared to the mode of the case without the barrier. But then you also increase the long trajectories because they stay here for longer. So if you have a unimodal probability, you have an increase in the mode, an increase of the tail, somewhere in between has to have decreased. No? If I show you, the actual probability, so that's the case where, you know, that's precisely this case when it's to the left. The mean is always the same, but you can see that as you change the position of the initial condition of u, so it's always, you know, n0 is 8 here, u is changing between 1 and 7. So as you can see, you increase the value as you get closer and closer. So when it's 1, it's closest to n0. You increase the mode, the maximum, but then you also have the tails, which are much longer, no? Because you create lots of space to the left. And then if you instead you put yourself closer to the reflecting boundary, you just increase only a tiny bit, and then correspondingly also this. And this is the intermediate regime, if you want, where you have to increase. So this is an example where you have a function where it depends on one parameter, you change it, the mean stays always the same, but all the higher moments will change. So it's quite surprising mathematically. Now, there is also dependence when you put this barrier on the right, which is, here you have the mean is going to change. Okay, I'm not going to tell you much about that. So, okay, this will be to explain you how, so the details, how you compute the actual, why is exactly the mean exactly doesn't change. Okay, I don't have the time. So what I want to tell you, maybe just to finish, because I see I don't have so much time, I just want to tell you about going beyond Smoluchowski. So imagine you have the classical 1D problem, and we want to consider the permeable barrier. So what happens to the diffusion equation? Now, again, here we exploit the possibility of working on discrete. Well, in this case, I start from continuous time, not much difference. So, and the way you write this problem is that you have the usual part here, which is the usual diffusion in discrete space, and then you change the diffusion equation by this structuring of a delta, which is the difference of the probability little f, which is a bit smaller than the capital F, which are throughout. And you can, you can actually look at the precisely, if you put this Kronecker delta here, that's exactly what you get, so that it represents precisely what you see here. These are the rates to go from left to right, right to left here. No? So now you take your limit here, the usual continuous limit, and then what you get the permeability, which is given by F. You make F very large. So I haven't put that. You need also little f very large, A small, you get your permeability. This is a unit of velocity. And it turns out that you can show that what you get in this specific case, you get an additional term which actually depends on the current. Now, the usual case when you have reactive defects, you get minus some rate, a Dirac delta, and the probability at that point. Here, instead, this is was not known, and so that's what you get. And then you can just show that automatically this satisfies the so-called leather boundary condition, which is the one related to permeable barrier. And of course, this is valid also if you have, the Smoluchowski equation here. So I guess that really I should stop because I'm probably already over time. So let me just go to the get stuck. Yeah, here. Oops, where it is. There to the references. So some are so these are the one published. I told you a bit about this. I use some of the results here. About infection transmission, there was this paper. This is the one about the Smoluchowski, the change, the new equation beyond Smoluchowski. This is about the inert interaction, and a little bit about no, actually I haven't mentioned at the end. None of this. So, but now this is the book I published 2021. When there is a pandemic, what you do? You write books, no? So okay, that has nothing to do with discrete space, but okay, in case you're curious. Thank you so much.
Thank you very much. Now, we are running slightly over, so if you do need to go, please do. But we can hang around for a few more minutes for a couple of questions. Is there anyone who wants to kick off?
Hi, Luca. Very interesting. So I guess I want to know how does the difficulty of things scale with your size of your lattice?
Oh, very good. Yeah.
So like what happens as you go to larger and larger n?
Yeah. So so the computation scales as there is a memory aspect and there is a determinant. The calculation of determinants is, suppose you have an m by m determinants, is m to the power 2.7, I think. That's how it scales. Given that you have all the elements in the, because it's not a sparse matrix, it's a dense matrix. Now, for the value of each element of the matrix, there are ways to try to approximate and so on, but it's a memory aspect, and it scales as m squared. Okay. So now that one you can parallelize easily. You can use GPUs, and that's for example, the figure on the transmission for the reflecting figure 3 days, GPUs, I mean, not the super fast one. Now the periodic, there are techniques. The periodic was exact. I mean, I didn't have the time to tell you how you make it exact. It has to do with the position of the target, which are perfectly periodic. But that also happens when you have a random distribution of targets. So there are ways not to compute. So when it's exact, I'm saying a minute, because you don't have to compute the determinant. So you bypass the computation of the determinant. So that approximation on a reflective lattice, it's a good one, unless you are in the predator-prey problem where there was highly asymmetry there. If you meet on all over space, this approximation I call the new approximation is pretty good, and therefore I would bypass all of what I just told you, which is exact. I hope I've answered enough, Daniel.
Yes, yeah, I more or less got it. Thanks.
Great. Any other questions? So I have one about the thigmotaxis example. So we had this insect that went around and around the outside. What if you put the insect into a non-convex shape? What does it do?
Very good question. Yeah, interesting. Okay, maybe the rat would figure it out and follow the termite. I'm not sure. No, it's interesting. Why would they always do? I think it's the reason they always do it in the circular shape, at least for the insects, because it's easy to build them. No, if you want the but yeah, no. So the real answer, Daniel, is I don't know. I don't know what the animal would do.
Great, but and therefore what the model would predict it should.
Yeah, yeah. No, yeah. I would have to do it. Yeah, yeah.
Cool. Okay, well, we'd better wrap up.
Yeah.
Thank you very much again. That was a fascinating talk. I really enjoyed it. In 2 weeks' time, we have another seminar by Sene Sokulu, and she'll be talking about more is better or not, an empirical analysis of the buyer preferences for variety on the e-market. So a bit of a change in topic. But yeah, thanks very much, and see you next time.